Okay, webinar is live.
Thanks, Gareth. Can you end the practice session?
Yeah. Practice session is ended. It is live.
Welcome everyone to today's SANSA Space Talk webinar. We're just going to give everyone some time to join the webinar and we will start shortly. Thank you. Okay, thank you very much everyone for joining today's SANSA Space Talk webinar. Today we have a very exciting topic ahead of us. Prof. Mike Kosh is going to talk about atmospheric optics, rainbows and other magical lights. So let me introduce Prof. Mike Kosh to you. Prof. Mike Kosh was born and raised in Durban in South Africa, where he also achieved his BSc Electronic Engineering in 1984 and PhD in Space Physics in 1991, following a life-changing experience overwintering at the Sinai Antarctic Research Station in 1984 to 1986. He was based for over 2 decades in Europe, first as a postdoc and scientist at the Max Planck Institute in Germany during the 1990s, and then as a lecturer, professor, and experimental space science faculty research dean at Lancaster University in the UK during the 2000s. He has held research fellowships in Australia 3 times, Japan, and twice USA, as well as many research visits to Norway. Since 2014, he is the chief scientist at the South African National Space Agency in Hermanus, managing the space research and applications group, including the Space Weather Unit. He also co-directs EnviroVision Solutions, a spin-out company specializing in rapid wildfire smoke detection with a focus on forests. His research is mainly focused on auroral physics and in the electrodynamics for the polar upper atmosphere. So, as you can see, Prof. Mike Kosh is quite an illustrious scientist and has a very decorated background. And for those who know him also as the Director of Fun here at SANSA. And with that, I would like to hand over to Prof. Mike. Over to you. Please take it away.
Right. Thank you very much, Darlene. And I've taken quite a broad interpretation of the title. We're going to have a look at a whole range of interesting optical phenomena that are in the atmosphere that many of us could see on an almost daily basis. And the way I've structured the talk is roughly in altitude, things that you can see near the horizon in the beginning, and then things later you can see higher and higher in the atmosphere. So first up is the so-called green flash. And the green flash occurs very briefly at around the time of sunset or sunrise. You have to be viewing the distant horizon, a true horizon, which typically would occur over the ocean, and a very distinct green spot will be visible for about 1 or 2 seconds on the upper rim of the sun when it's either rising or setting. And these green flashes are due to atmospheric refraction, causing sunlight to separate into different colors. The very bright red and yellow colors of the sun are refracted to below the horizon, leaving the dimmer green and blue colors visibly above the horizon as it moves. And you can see in the little animation how refraction works. It's bending the light as you go from one refractive medium to another. The picture at the top shows you the little green flash, which is just the top of the sun as it is setting, and the panels below show you a sequence of events. You can see yellow with some green, then yellow, and then green, more green, and then even a hint of blue as the sun goes down. And this can be seen on any clear day when you look out at sunset, preferably over the ocean. Next up, a little bit higher, are so-called light pillars. And there are two illustrations here. The one at the bottom right are light pillars caused by street lights or artificial lights. And you can see that each pillar then takes on the color of the light source itself. But you can also get it quite naturally. This picture here on the top left shows a light pillar associated with the sun, and I'll talk about the halo later. Now, in this presentation, I have used as many photographs that I have taken myself as I have. And this is a particular example. This was from my time in Antarctica at Sanai Station in 1985. I took a picture of the sun pillar here with the halo around it. What causes sun pillars? Well, sun pillars are, or light pillars, sorry, are created by the reflection of light from many tiny ice crystals that are suspended in the atmosphere. And the crystals responsible for these light pillars usually consist of flat hexagonal plates, which are drifting down. So they lie horizontally in the atmosphere, millions of them, and they tend to drift down. And each flake acts as a little tiny mirror. So the light source is reflected. In this case, in the example shown on the right, you've got a street light. It's reflected from the many, many tiny little mirrors floating in the sky. And then you see that reflection from the ground from where you are standing. And because the flakes are at many altitudes and are drifting down, we tend to then see a vertical column of light projected into the sky in front of us. It's virtual. It's not actually a real source of light, as indicated in the diagram. So it's an ice crystal phenomenon. It has to be cold air. Next up is the solar glory. The glory is generally caused by sunlight. It can also be caused by moonlight, but it will be very faint. And this is interacting with many tiny water droplets in the air, usually when there's fog or mist or clouds. And the glory consists of one or more concentric rings, as is shown in the figure over here, where red is on the outside and blue is on the inside. And glories are due to wave interference of light, which is internally refracted within small water droplets. Usually, the inner angular size of the ring is about 5 degrees around the shadow point, and the outer is about 20 degrees around the shadow point. This example here in this figure is a photograph taken from an aircraft, and you can see the shadow of the aircraft on the cloud at the same time. But you can even get a glory around your own head. So for example, if you're standing in a fog or a mist, say on a mountain, and the sun is behind you, a glory can occur. The center of the glory will always coincide to the shadow of the observer's head. So that means that the clouds or fog causing it must be located below the observer so that the sun or the moon is in a straight line behind your head or your observing eye, which is the reason why the so-called glories are commonly observed from a high viewpoint, such as a mountain or a tall building, or from the window of an aircraft. And then next up is a rainbow. This is a photograph of a rainbow I took many years ago in New Mexico in the United States. You'll have all seen rainbows before. You normally get a single rainbow shown over here where red is on the outside and blue is on the inside, yellow and green is in the middle. But sometimes if the rainbow is particularly intense, you can see the double rainbow, and that's shown over here very nicely. And note that in the double rainbow, the colors are reversed. Now you have red on the inside and blue on the outside. And the way a rainbow works is as follows. In a case of a rainbow, the sun will always be behind you. So you've got to have the sun behind your head, and then you see the rainbow at the anti-solar points. So you've got the sun above you or behind you, you're down over here. The anti-solar point is the ray parallel from your head in the direction that the sun rays are pointing. And then those sun's rays can follow one of two paths. On the top right, what happens is the sun's ray enters every single little water droplet. Where you go from air to water, there is refraction. Then the ray goes to the back of the water droplet. And at that point, you get total internal reflection, and I will come back to that in a moment. Then the ray reflects back towards the observer, and where it goes from water to air, it undergoes refraction again. So there's three processes going on here. Twice there's refraction at the water-air interface, and once there's total internal reflection at the back of the water drop. And this is different for different wavelengths. So the primary rainbow will appear to the observer around 40 to 42 or 43 degrees from the anti-solar points. If the light ray enters the water droplet at the bottom, as shown over here, then you're going to get one set of refraction, 2 times internal reflection, and then one set of refraction again. So twice refraction, twice total internal reflection. Now the ray is reversed, so that explains why the colors are reversed, and the angle that you see the secondary rainbow at is around 50 to 53 degrees away from the anti-solar point. So it explains why the colors are reversed in the second rainbow and why the second rainbow appears further out than the first rainbow. And we can see this very clearly here. This is shown at the top left very nicely, how the ray comes in. You get refraction at the interface between air and water. Then you get total internal reflection at the back. Then you get refraction again. All the while, the different wavelengths spread out. And the angle is described by this little formula here. That's Snell's law of refraction. We know the refractive index of air is about 1, of water it's about 1.3. So then you can do the calculation for the angles. And if you do that, you see very clearly how the blue would be coming out at around 40 or 41 degrees, and the red would emerge at an angle of around 42 or so degrees. Now at the back, you get total internal reflection. That's just a special form of refraction. It means that the refraction angle is 90 degrees or more. So here at the bottom left diagram, you see the first 2 rays show normal refraction. The last 2 rays show total internal reflection, where the angle of refraction is more than 90 degrees. And that's given by this little formula over here. And for water and air, where we know the refractive index is 1 and 1.3, the critical angle for achieving total internal reflection is 50 degrees. It's exactly the same principle that is used for fiber optic communications that we use for internet and telephone everywhere in the world for sending signals down fiber optic cables, and also explains why the rainbow has the colors they have and the position that they have. Next up is the 22-degree halo. These are 2 photographs of halos taken by myself. The one on the left is taken at South Pole. We did that in 2016. And the one on the right is taken at Sanai, Antarctica in 1985 with the moon. In both cases, the angular circumference or diameter of the halo is 22 degrees. You have to look into the sun or the moon, so with caution, and you can see that the red color is on the inside, therefore the blue color would be on the outside. And the 22-degree halo basically is as the result of refraction by millions of ice crystals, hexagonal in shape, and they're suspended in the atmosphere or drifting in the atmosphere with random orientation. And this phenomenon can be seen anywhere in the world in any season, as long as there's ice crystals in the atmosphere at the apparent angle or height that the sun is. So you have crystals that are hexagonal like this. Light enters the crystal from one side, it refracts at the surface, it goes through the crystal, and then it refracts again at the other side. And that gives you the circular pattern. And because the refraction for different wavelengths is different, you also get the color separation. And 22-degree halos are fairly common, and I've seen them quite often. You just have to keep an eye out for them. Then we have the special case of the 22-degree halo called the sundog or Parhelion. On the left is the photograph taken by myself at South Pole. I've used a colleague, his head basically to block out the sun. And you can see very beautifully two bright patches, one on the left and one on the right. The photograph on the right was taken in Alaska, again by myself, and you can see quite a close zoom up of a sundog. It's red on the inside and then more bluish on the outside. This angular separation is also 22 degrees. So the sundog is a special case of a 22-degree halo, also caused by refraction of sunlight by hexagonal ice crystals. But in this case, the ice crystals are lying horizontally. So if they lie horizontally, then the light will focus on the horizontal position around the sun at the height that the sun happens to be at. As the sun goes up and down, the sundog will also go up and down. So they always come in pairs. They always appear at the same altitude as the sun above the horizon. And again, they can be seen at any time, anywhere in the world. So this is again a photograph by myself from Antarctica in 1985. Clearly you can see the sundogs, but you can also see a hint of the halo. So that means that most crystals were lying horizontally, but a few of them were randomly orientated. So you tend to see the halo and the sundog simultaneously. Next, we're in the clouds, iridescent clouds. This is a photograph again by myself when I was in Washington around 2005, but you can see iridescent clouds anywhere at any time. So cloud iridescence or irisation always appears somewhere near the sun. You don't have to look directly in the sun, but you have to look near the sun or the moon, as it turns out. And the colors resemble those seen on soap bubbles or oil films on water. And iridescence of the clouds is a diffraction phenomenon, which is caused by very small water droplets, mist or fog, or very small ice crystals individually scattering the light. So on the right-hand side, you see a photograph of an iridescent cloud. The pole is blocking out the sun, so we can take the photograph, and here you see the cloud with some red and green colors associated with it. So in this case, this was Antarctica in 1985, so it would have been ice crystals. And if the ice crystals are very small, or the gap between the ice crystals are very small, the light source, which is the sun, passing in the gap or over the crystals will undergo diffraction. That means that the rays of the light will go in different directions. Those rays then interfere with each other. You can see this ray will be touching that ray, and therefore, again, depending on the wavelength, you'll get regions of the sky which are brighter or darker at different colors. And that explains why this irisation of the cloud appears. And you can see that from clouds at any time, at any place. Now, these are special clouds. These are called Noctilucent clouds. Noctilucent clouds, as you see in this photograph over here, are composed of tiny water ice crystals and exist at very high altitudes. Normal clouds are up to 12, 15 kilometers altitude. but Noctilucent clouds exist around 76 to 85 kilometers altitude. They're certainly the highest clouds that we know that exist. They can only be observed after sunset because you need the sun to illuminate the cloud from below and to be dark on the ground so that you can see them. So soon after sunset, the sun will illuminate the clouds from below, and you often get these sort of white shimmering clouds in the sky. It is a high latitude phenomenon, so Northern Europe, Canada, Russia, and so on would see Noctilucent clouds rather frequently around sunset or sunrise. There have been no confirmed records of Noctilucent clouds pre-1885. So we know that this is a relatively new phenomenon that exists in the atmosphere, and it must be due to ice or water crystals turning into ice crystals at these very high altitudes, around 80 kilometers altitude. And we believe that their presence is an indication of climate change, because the transport of water to these altitudes, water from the ground will not get to those altitudes. The way you get water to those altitudes is through methane emissions. The methane is transported as a gas to high altitudes and then can be chemically converted to water. And we know that the main source of production of methane in sufficient quantities is through human activity, mainly through food production, for example, rice and beef, cows, through landfills, so rotting matter of all descriptions, and the emissions of coal power stations are the major sources of methane. And we know, these are measurements shown here at the top right, that methane has been increasing steadily over the decades in the atmosphere, in more or less in direct proportion to the human population, because all our activities need electricity, food, and so on and so forth, which produce rubbish and methane in large quantities. So it's a new phenomenon associated mainly with human activities. Now I move on to transient luminous events. As the name implies, they are transient, so they're short-lived, typically 1 to 10 milliseconds. And of course, they're luminous. That means they're very bright in the sky. So transient luminous events, or TLEs, describe a variety of mesospheric and stratospheric gas discharge optical phenomena. Usually they occur from below 100 kilometers altitude down to as low as 30 or 40 kilometers altitude, certainly in some cases really down to the top of thunderclouds. And thunderclouds are very important to this phenomenon. And there's a variety of them. We call them loosely sprites. Sometimes they have halos on top of that. And then you have the blue jet, which is at the bottom of basically a gigantic jet. And then you have a thing called an ELF, which is this phenomenon over here. You can see that they're rather large. They're typically of the order of tens of kilometers across, maybe as much as 300 kilometers across. And they would typically stand 50, 60 or more kilometers tall. They can be seen by the human eye, but very few people have ever seen one by the human eye, but it is possible. So what is a gas discharge? This is important. We will come back to this again when we talk about auroras. A gas discharge is where you have a neutral gas in our atmosphere. That will be oxygen and nitrogen. That molecule or atom is excited through some process, usually by a collision by another particle, typically a charged particle. So an electron may collide with an oxygen atom or a nitrogen molecule. It then excites that molecule or atom to a high energy state. That molecule doesn't like being energized. It wants to release that energy quickly. There's a number of ways it can do it. One of its favorite ways is to release that energy as a photon. Now, the photons that are produced, the color of the photons or the wavelength of the photon depends very much on the energy levels of the atom or the molecule. So this energy change here is defined by the type of species you're looking at, oxygen and nitrogen in our case. If you know the energy, then through this little formula, through Planck's formula, you've got Planck's constant, you've got the speed of light, which is constant. So by knowing the energy change from one state to another state, you can work out what the wavelength of light will be. And so for nitrogen, we can see what wavelengths will be emitted. There's a very strong wavelength in the red, above 650 nanometers. And then there's a set of wavelengths in the blue down here. The one that we're interested in is at 428 nanometers. But each species will have its own set of wavelengths. In order for a gas discharge to occur, the local electric field has to exceed the minimum voltage required for dielectric breakdown to occur, so that you initiate a gas discharge. In our atmosphere, starting at the ground all the way up to 100 kilometers, the dashed line shows the breakdown voltage required. So for example, at ground level, we would require about 3 million volts per meter. If you're up here at around 80 kilometers or so, you need about 100 volts per meter. So you need much lower voltage at higher altitudes. And we know, jumping the gun slightly, that if you have a lightning strike from a thunderstorm, you will generate a very large voltage of around 50 to 100,000 volts per meter. That voltage, that electric field, then projects up into the atmosphere as 1 over height cubed. That's the solid line here. Where that solid line crosses the dashed line, you're now in the regime where the electric field exceeds the minimum voltage required to cause a gas discharge. So transient luminous events always trigger with a lightning strike, and they always trigger around 80, 85, 75 kilometers altitude. And then once they're triggered, they can come down to lower altitudes. And the way this works is you have a cloud, you have a thunderstorm cloud, and we have lots of those in South Africa in January and February. The top of the cloud is positively charged, the bottom of the cloud is negatively charged. If you have a lightning strike, which goes from the top of the cloud to the ground, shown here, the positive charges disappear. You end up with a lot of negative charges. That generates a huge electric field. That electric field then triggers a sprite. Of course, very soon those charges disappear, and then after about 10 to maybe 100 milliseconds, it's all back to normal. So that discharge is very brief. We know that TLEs are associated with the Earth's, with the electric field associated with thunderstorms. Not only do they occur at the correct time, the lightning strike and the TLE occurs simultaneously, but the electric field from a lightning strike spreads out along these curved lines as shown by the figure at the bottom right. And if you look at the optics of transient luminous events, they always bend in towards where the lightning strike was. You can see the lightning strike would have been around here. It's illuminating the bottom of the clouds, and they always bend in following these lines of electric field force. Now, most lightning strikes are either inside the cloud or from the bottom of the cloud to the ground, and they are not interesting for this phenomenon. Only the lightning strikes from the top of the cloud, the positive ones, work for this. So we know some lightning basics, that lightning occurs about 40 or 50 times per second everywhere across the globe. That gives you around 1.4 billion strokes per year. Most of the lightning, about 70%, is over land, and a typical lightning current is around 30,000 amps. We know now from measurements that a transient luminous event requires about 70,000 amps, sorry, to be triggered. So it's only the really big lightning strikes that cause TLEs. So only about a quarter of all lightning strikes are cloud to ground. Of those, only 5% are of the positive variety from the top of the cloud. Of those, only 0.5% have a big enough current to set off a transient luminous event. So there's only about 2 million TLEs per year, around 3 or so per minute, but the problem is we don't know where they occur. So the map below shows where most of the lightning occurs. This is an average of lightning strikes taken over a decade. And you can see that South Africa, shown here in the red circle, is a lightning hotspot, but only in the period around December to maybe March. We have a lot of lightning in this country in our summer. So just before I show you some examples, the TLEs were predicted by a gentleman called C.T.R. Wilson in 1925. He won the Nobel Prize, but he never saw a sprite or TLE. These were first observed by complete chance in the United States on the 6th of July, 1989, which is amazing considering that lightning's been around for millions of years. Certainly in the entire time that humans have existed, lightning has existed, and yet we only saw them for the very first time 30 or so years ago. The picture you see here on the bottom right is a real picture of a real sprite taken from an aircraft. It's the first known color picture of a sprite taken from an aircraft in 1994. And this is very typical. The top part of the sprite is red. So that's the strong emission from nitrogen. And the bottom part of the sprite is blue, also from nitrogen, mainly N2+. Sorry, I don't know why it's moving. And then this bright thing at the bottom here is the cloud, which is illuminated below by the lightning strike. So the sprite consists of many streamers, typically 60 to 200 meters across, and they all add up to this phenomenon, which may be tens of kilometers across and tens of kilometers tall. The emissions are mainly in nitrogen, so the red, as I mentioned already, the blue, as I mentioned already, and the UV. We can't see the UV emission from the ground because the ozone layer is around 30 kilometers altitude and blocks the UV, but you can see it from space, no problem at all. And sprites often occur in clusters. You see a hint of 2 other sprites in this photograph here. So we've done some field work in South Africa. Starting in 2015. These pictures just show some of the stuff that we've done. This is our site out at the South African Astronomical Observatory in Sutherland in the Northern Cape. We've also done observations from the SKA site at Carnarvon, which is about 200 kilometers from the Sutherland site. You can see here one of my students, DeCarlo, on the left, and one of my guest visitors, Martin, on the right. And the instrument they're working with is measuring the electric field associated with the lightning strike, as well as the sprite. We've also measured the magnetic field associated with lightning strikes and sprites using these induction magnetometers. And then we have a collection of 5 cameras. Here you see 4 of them mounted on a tripod together. The 5th one was at another location. 2 of the cameras have filters on. You can see the filters on the cameras that are in the middle here for red and blue. And then the 2 smaller cameras are white light. We use those to locate the sprites before we zoom in with the other cameras with filters. And these are some examples of sprites that were taken. This is from Sutherland, taken in 2019. And you see very beautifully what we typically would call carrot sprites. So the cloud is illuminated from below by the lightning strike. You see the streamers over here. You see the main body of the carrot sprite, and then you see the sort of halo or fuzzy thing at the top. The top will be around 90 or so kilometers. The bottom may be as low as 50, 40 or so kilometers, and the brightest region in the middle is around 75 kilometers. You can see very clearly they may occur in clusters. There's a set of a cluster of carrot sprites there. Likewise, a cluster of carrot sprites over there. And again, from Carnarvon 2019, we can see lots and lots of different types of sprites. So this is a carrot. Next is column sprites. They always come in a cluster of columns. Jellyfish sprite. Halo, sprite with halo. You can see the big halo at the top here, the fuzzy thing at the top. Bottom left, wishbone sprite. Tree sprite because it looks like a tree. Angel sprite because it looks like an angel. And then sometimes we just don't know what it actually is. So the different names just are giving you the different types of sprites as recorded by cameras. We have also we have recorded hundreds of sprites over the years in South Africa, but it's extremely difficult to record sprites, the same sprite, from 2 different locations. So we've done this maybe about 10 times, where we had cameras running at Carnarvon and Sutherland simultaneously, and you can see very beautifully this sprite over here is exactly the same sprite as recorded by the other camera in the other location. And this, of course, allows us then to triangulate the sprite in terms of its horizontal position and also its vertical height, and get its association in time and in position with the lightning strike. The lightning information we get from the South African Weather Service. So I'm going to run a little video now. It's been heavily edited, so those flashes that you see are the sprites. And you can see the stars as dots in the background. The stars will move because we've taken away the long periods of boring nothingness. And you'll see the sprites as flashes as recorded by the night vision TV camera. These particularly dark images is because we used a filter. So the filter has removed the background and most of the stars. The trees are just there by sheer bad luck. The sprite is in between the trees. So that's what a typical video recording of a sprite would look like. It's very hard to see a sprite with the naked eye, but you can see them very easily with a night vision camera of the sort that we have. So moving away from sprites, we now address Airglow. Airglow is a faint emission from the upper atmosphere, which is present all the time and present everywhere on the globe. And it typically occurs in the height range from about 85 kilometers to 300 kilometers. It's basically a chemical reaction due to the atmosphere is energized during the daytime by the sun, and then of course relaxes at night when the sun sets, and some of that energy is released in terms of photons. It's quite dim, you don't really see it with the naked eye, but it does mean the sky is never completely black. So this is a picture taken from the International Space Station. You can see very clearly the Earth below with the lights of cities and so on and so forth. You can see the horizon, you can see the sky background, which is very black, and then you see this band of green in this case, which is clearly the Airglow layer. In this case, that green emission comes from atomic oxygen at a height of around 97 or 100 kilometers. The lower height at 85 kilometers is mainly infrared emissions from the OH molecule, that's the hydroxyl molecule. And then above the green, very faint, but so you can't see it here, around 300 kilometers altitude, we get a red emission, which also comes from atomic oxygen. And we can use these Airglow images using a special camera. This is an Airglow imager. We have one at Sutherland here in the Northern Cape. You can use that imager with filters to image atmospheric gravity waves. And these are 2 examples. So the one on the left is from the red emission at around 240 kilometers, and the one on the right is from the infrared emission at around 85 kilometers. And you can very clearly see the wavy structure that is in here. This is a fisheye lens, so the field of view is 180 degrees field of view. So in the case of the red emission, the distance across the image is about 2,000 kilometers. And these bands will move across the image over time and in the night. And you very clearly can see that gravity waves exist and that they propagate. You can also see the stars, and in this case over here, you see the Milky Way at the same time. So then moving on to auroras. Auroras are definitely a high latitude phenomenon. They're extremely rare in a country like South Africa. I think the only time I know that they've been observed was in 1989. Auroras are caused by electrons and protons, which come from the sun, becoming trapped in the Earth's magnetic field. They then travel down the magnetic field lines and crash into the top of the atmosphere. And that basically causes a gas discharge. You are energizing the oxygen and the nitrogen of the atmosphere. It then releases photons, as I described before. And auroras can be seen in many different forms: bands, corona, diffuse, arcs, rays, draperies, and so on and so forth. The rays show very clearly the orientation of the Earth's magnetic field line, tilted as it is over here. And the different colors are due to the different constituents, the gases of the atmosphere. So typically we would see green at around 100 to 150 kilometers altitude, and we would see red at altitudes from around 200 to 500 or 600 kilometers altitude. The red and the green comes from atomic oxygen, excited atomic oxygen. The blue colors or slightly purple colors come from molecular nitrogen, but both of them are excited by impact from electrons or protons. So here's some more photographs of auroras. This is the one at the top left is from Lancaster in the north part of the United Kingdom, 2005. This is my other work location, and you can see very beautifully aurora here with rays, the red on the top and the green on the bottom. The photo on the top right is from Svalbard, 1899. This is the very first known photograph of an aurora that was made by the Russian expedition in that year. And you quite clearly see it's black and white, of course, the aurora there in the background. Bottom right is a photograph of aurora taken from the space shuttle. You can see quite clearly the space shuttle on the left and the aurora in the distance. And then bottom left, this is a photograph taken by myself in 1985 in Antarctica, a quiet auroral arc. You can see the exposure is very long. It's about half an hour because the stars form streaks in the sky during the time of the exposure. Now, auroras occur in an oval region on the Earth. You can see bottom left, the oval over here. In the northern hemisphere, you can see from the satellite photograph bottom right that the oval occurs in the north and the south simultaneously. And then the top pictures show animations from satellite imagery of the auroral oval. So this is the one shown over Antarctica, beautifully over time. And this one top right shows the auroral oval also over time, simultaneously in the north and the south. So we would normally see the same auroras in the north and the south simultaneously. Obviously, it's difficult because you can only see auroras at night and usually in winter, and the other hemisphere is in summer. So it's difficult to get that right. And we know that the auroras will only occur in polar latitudes because the electrons and protons that come from the sun are trapped on the Earth's magnetic field. And it's only where the Earth's magnetic field comes down to the atmosphere or down to the ground, which is only near the north and the south poles, that auroras can occur. Auroras cannot normally occur anywhere near the equator or at low latitudes because there's no path for the electrons and protons to travel along. They must travel parallel to the magnetic field. They cannot cross the magnetic field. So that explains the ovals and also why it's at polar latitudes. We know that auroras also occur on other planets. These are photographs taken by satellites. This is the one for Jupiter, north and south. This is the one top right for Saturn. Again, you see the oval structure and you see the auroras occurring at the polar regions of both Saturn and Jupiter. We also have another phenomenon called the black aurora, which I have studied. This is a photo taken by myself in Norway from 2002. You can see this black arc-like structure, and this is at around 100 kilometers altitude. And it's a very intriguing phenomenon. I'm going to run a small video now to show you what a black aurora looks like. So the dots are stars in the background. Time is running at the top of the screen, slightly faster than real time. And you can see these black structures. So not colors, not bright, black structures moving around in the sky. And these are what we call the black auroras. Okay, they're typically a few tens of kilometers across. Normal auroras can be hundreds to thousands of kilometers long. Black auroras tend to be a bit smaller, but they're very intriguing and interesting phenomenon, not yet properly understood. So I'll move on. And then in a discovery that was made by ourselves, so this was basically by Nell. She was a PhD student with myself, and we published this last year in 2021. We were studying the black auroras, and then we discovered the so-called anti-black auroras. So you can see the black auroras very clearly here. These are these black patches, and they're moving from right to left. But every now and then, a black aurora will have a white patch that runs right next to it. And you can see it's moving, and over here, it even flips to the other side of the black patch. So as the black patches move, the little white patch on some of the black auroras move exactly in parallel with it. So in this discovery of what we now call the anti-black auroras, so it's not a normal white aurora, was published by Nell and myself last year. And then finally, the artificial auroras. I've led a very long and major campaign, both in the United States and in Europe, generating artificial auroras. So basically auroras on demand. I'm going to run the video now, and then I'll explain later. So this is a fisheye lens. So 180-degree field of view, north, south, east, west is indicated on here. This was recorded in Norway in 2013 by myself. And I'll just start running the video. The yellow is basically clouds. The green is natural auroras. And this red spot in the middle here is an artificial aurora generated on demand. There we go. So we can turn the generating mechanism on and off on demand. And of course, we're limited in the amount of the sky that we can illuminate. This is the moon here at the top left, just going down. And then these lights here at the horizon are basically an ionosonde mast. So the way we generate artificial auroras is that we use a thing called a heater. This is the EISCAT facility in Norway. Basically, to give you the scale, this is an antenna field. It's about 500 meters on one side, so 500 by 500 meters with a transmitter in the middle. We have two radars. This radar is 120 by 40 meters, and the small radar is 32 meters. So this transmitter, we can generate, we have a 1.2 megawatt transmitter, and we can focus the beam of that transmitter to generate a very high power narrow beam. The maximum effective radiated power being about 1,200 megawatts. This is the equivalent power consumption of 600,000 homes all running simultaneously. So the amount of energy that's being transmitted out of here is more than the power that would be consumed by 500,000 homes on a normal day. It's a radio wave that you're transmitting. That radio wave carries an electric field with it. It's an electromagnetic wave. That electric field is transmitted up into the atmosphere. When you get into the ionosphere, where you have electrons and protons, they are charged. They respond to that electric field in a very special way. So here we are, we use the heater, we transmit a high power electric field into the upper atmosphere. When that electric field gets up into the ionosphere, typically around 200, 250 kilometers altitude, you can set up a resonance. So your ambient electrons are now oscillating with the frequency of the wave if you've chosen it correctly. So it's like a vibrating tuning fork. You give it a bash and it sings. Once you set up waves in the ionosphere, in the plasma of the ionosphere, those waves, if they're the correct type of waves with the correct frequency, can then accelerate the background ambient electrons. So it's like a surfer on the ocean. You have waves generated one way or the other. Those waves allow the surfer to go from stationary to high speed. You do the same thing with the electrons. Once those electrons start moving, they then collide with the oxygen and nitrogen in the background of the atmosphere. that then produces photons. Those photons we can image. So we are basically imaging wave plasma interactions. And this is another example of a wave plasma interaction. We can see the optical emission there recorded by myself in Norway in 2001. And this is about 30 kilometers across. So this gives you a sort of idea of the size, 30 kilometers across at an altitude of around 200 or so kilometers. And this experiment, we ran these experiments around the period, around solar maximum 1998 to 2002. I managed to burn about 1,000 operating hours on this experiment, which was funded at that time by the Max Planck Institute in Germany and also Lancaster University in the UK. Each operating hour is worth about, depends on how you configure the system, between 20 and 50,000 Rand. So that experiment that we ran consumed over a 4 or 5 year period at least 20 million Rands worth of experiment time. So it was a very exciting and also at that time a very important experiment. And we ended up producing maybe as many as 50 publications out of this particular experiment. And boy, was it fun. I had a great time going to the Arctic and making artificial auroras appear. It was absolutely huge fun. And that's the end of my presentation. Thank you very much.
Thank you very much for that fascinating talk, Prof. Prof. Mike. That has really been very interesting and very insightful. So I will now open up the floor for questions. Please go ahead and put your questions in the Q&A box. We have some time to address some questions. So please, if you have any questions for Prof. Mike Koch, please do so now. While you are typing out your questions, please also follow us on our SANSA social media sites. We are on Twitter, we are on LinkedIn, and we are also on Facebook. And if you follow these sites, you will see there that we post regularly also about this webinar series. And then you can follow the webinar series and our next webinar. We will have our next webinar at the end of the month. Okay. I don't see any questions coming in at this stage.
Well, if anyone's interested, they can always get hold of me after the fact.
Okay, here's some questions. Okay. Jaco van der Walt asks, do you have any explanation on ball lightning observed on the surface of the Earth as well as in the air with airplanes?
The answer to that is no. I have personally never encountered ball lightning. I know it exists. So the honest truth is I would have to research it up to find an answer. But my suspicion is that nobody really knows. And that's the problem with phenomena that are fairly intermittent. If you aren't able to record enough of them, it's hard for you to know what's going on.
Okay, and then Sarah asks, there are reports of luminous phenomena being observed at the time of earthquakes. What do you suppose these earthquake lights are?
Right. Again, I don't really know, but I know that earthquakes obviously result in huge stresses in rocks and in the ground. And it's a well-known phenomenon that charged particles are released, charged gases are released from earthquake events. So it's not beyond the realm of reason that these charged gases, which would be released from earthquakes, would then have a chemical reaction with the rest of the atmosphere and produce luminosity, presumably at night, you know. So I expect it's very real, but I don't know the details.
Thank you very much, Prof. And then Johan Prinsloo just says, just a great big thank you.
Thank you. Yeah. Just keep your eyes open. I mean, it's amazing what you can see by just looking up semi-constantly. Most people are looking down or not looking anywhere useful. If you just keep your eye on the sky, it's unbelievable what you might see sometimes.
Well, there you have it, folks. Please look up. Thank you very much for your sharing your knowledge and insight, Prof. Maikosh. And thank you very much, everyone. Okay, before I go, okay, there's another big thank you for the presentation. Thank you, everyone, for joining, and keep an eye out for our next webinar. See you next time. Goodbye.
Thank you. Goodbye, and have a good day.